All right, so and dive into things here. Um, the first thing we'll take a look at is Canvas, and I am about 3/4 the way grading exams. Um, Obviously, the Canvas issue caused a bit of a disruption yesterday, so I lost some time being able to work on these. But hopefully you saw I was able to kind of email all of you not through Canvas. So hopefully you saw that email. That take home portion was supposed to be due at the end of the day last night. Basically didn't have the whole day to work on it. So if you were planning on that, it kind of caused some issues. You didn't have access to anything that was on Canvas. So if you had planned to use those materials, you couldn't do that. So I moved the due date to be the end of the day today. So if you haven't done that already, I can see there's still a good portion of people who haven't. Make sure you're getting that submitted by the end of the day today at 11:59. So once you start, you've got 60 minutes, which means you just start by 10:59. Okay. Of those who have done it, I'm seeing most of you got vast majority of the points on that take home portion. That was my intent, right? You have a lot more time. You have resources available to you. The in-class portion is a way for me to use time, right, to kind of test what your knowledge is without resources as well. So I'll end up, once I get these graded tomorrow, I'll kind of add those two together. So you should have your score by the time we start class for sure on Thursday. In fact, I'll likely get them posted sometime tomorrow afternoon. I'll hand those exams back on Thursday, the in-class portion. So I'll get here early. So I'll probably start handing those out before class starts, just so we can kind of try to get started a little more on time. As I'm grading them, there's some real easy points that people kind of left on the board by, I think, not reading questions carefully or kind of just assuming what I wanted based off of maybe previous exam questions, which I'm sure my previous exams are floating out there somewhere. I changed them. So some of the answers seemed a little bit odd because they weren't really even what the question was asking you about, right? It's not going to bode well because you then lose the vast majority of the points, right? So I don't care if you use old materials, but realize you're not going to see the same exact exam, even if it looks similar at portions, right? So reading those questions carefully, once we get to that final, that's going to be really important. You're leaving a lot of points in the, okay? Now, one thing I can do with this midterm, and I haven't decided exactly how I'm going to do this yet, so I'll have more information on Thursday. So based off of the grading through the first 75% of the in-class portion, I'll probably have a way in which you can gain back some of those points, right? So whether that is corrections of certain problems, whether or not that is a set of similar questions that you work through and then kind of provide answers to me within probably the course of a week. I'll have a little bit more details about that on Thursday's class, but I'm kind of anticipating there will be some way to at least earn back some points. Not every point or not, but kind of getting that average where I want it to be, which is usually somewhere between a 75 and an 80. Once again, I don't know how much of that I'm going to need to do because your take-home portion did very well. At least those who have submitted up to this point. I realize the average could fall there, but I'm thinking that, there will be some type of a small assignment that I will have available for the day where you can earn back some points on that exam. Okay. That won't exist for the final, so it makes kind of, this is a learning tool. I want you to learn this class. I don't care about shouldn't say it this way. I don't care about what grade you really get. I really care that you're learning this material. And so trying to game the system, like I said, looking at previous exams, it doesn't help if you don't understand the material and you don't answer the actual questions I'm asking, right? So whatever assignment or whatever way I provide you to get points back, it's going to be a way in which you can learn from your mistakes. That's the best way to learn. So I'll have more information about that on Thursday. I'll have those exams ready to kind of hand back. Other than that, we're going to jump right back into things, kind of where we left off. So I sent out a link, but now we all have access to Canvas again. So we'll have a lot of different data sets we use this week. Start looking at nonlinear relationships. It's also amazing. I saw a lot more friendly faces on Thursday than I do today. I'm going to run a couple regressions myself, controlling for some factors in this class, and probably have some results for you on Thursday as well. And maybe look at the coefficients of in-class attendance. I'm just going to go out on a limb and guess what those signs of those coefficients are. But I can't stress enough. I think being in class for this stuff, again, it's difficult, especially when we're working through the stuff in Stata. If you're trying to teach yourself this on your own using Google, once again, seeing assignments that like you're clearly not trying to mimic what we did in class. You're clearly trying to mimic something that you're throwing into an AI generated bot, and it's not accurate. So attending classes is really going to be important as we get closer to that final exam. Okay? So that's my spiel, right? The other thing I did want to mention, just because I think it's interesting before we jump into material, and we're like economists. So do you all know why Canvas was down?
Was it because of AWS cloud storage?
Yeah, so you saw AWS. Yeah, so I teach like basic intro micro, and I was thinking about this. So I didn't realize that Canvas topped all the other program platforms. A lot of them use Amazon's, like, I don't understand all the tech side of it, but like basically their infrastructure, right, to run something as big as Amazon. What do you think is probably true about the cost of that infrastructure? It's insanely high. You have to have a team of coders who are ready to fix things immediately, right? Because if you don't, you're not selling a lot of products, and that generates a lot of money for Amazon. So what's interesting to me is basically that's a fixed cost, right? Canvas actually doesn't have enough money, despite how many universities they're at. They actually can't pay for a large enough web-based infrastructure because they would need one that's large. Like, it's a huge fixed cost. So what do they rely on? Someone who already has something set up to that, who does a much larger quantity, right? They're scaling up production. Amazon's scale of production is way further down that average total cost curve. So what does Amazon do? Well, if they just use it for themselves, what are they not doing with that infrastructure? Selling it to other people. So what does it become? Opportunity cost, something you're foregoing. So how do they reduce their implicit costs, therefore increasing their economic profits? They take this infrastructure they've already paid for. It's there, fixed costs. It is what it is. By not selling this web space or web-based infrastructure to other companies, they're essentially leaving money on the table. So by selling part of that to the Canvas, what have they done? They've lowered their implicit costs. They're no longer foregoing much money. It's also interesting to me how their team of coders, I'm sure if something goes wrong with Amazon's website, you don't ever notice it. It's not generating as much money like Canvas. It takes a little bit longer to fix it, right? So incentives matter, right? It's at the end of the day. But we're back up and running, so we should be kind of good to go here. So I've got the slides pulled open. We'll kind of start jumping in right where we left off, unless you guys have any other questions for me related to the exam or anything along those lines. Okay. I'll put up an announcement after class, and I think you guys have been a lot better about this. Because the due date changed, it might have auto-filled some zeros. If you try to go to I haven't taken it yet, the take-home portion, if you go to the grade part of Canvas, like click on grades and look at the assignment, it looks like you've already submitted and it won't let you in. You actually need to go to the quizzes tab or the tab and click on the actual assignment. You go through the grades kind of tab, it won't open it up for you. So you have to either go through the quizzes tab or click on the actual take-home portion quiz, right, on the homepage. Okay. I've gotten no emails from any of you, so I'm guessing it's because you're juniors and seniors, and you've probably figured this out from other classes before. You would not imagine my inbox how many of those emails I've gotten from my 251 students. So other than that, I don't think that there's any other housekeeping stuff. You have a question? Or not? We're good? Okay. So where do we kind of leave off? So the vast majority of what we were building up to and the types of questions we were looking at on that exam were all linear regression, right? Even if it was multiple linear regression where we started controlling for other things, right? Multiple variables on that right-hand side, we were always assuming that the effect was a single value. So we are always assuming that when we're looking at this scatter plot of data, whatever X variable we were looking at and whatever Y variable we were trying to predict, we had this scatter plot of data. And sometimes maybe a scatter plot looks something like this. Well, if I can try to get a line that minimizes the sum of the squared errors. So it's trying to minimize the difference between the actual Y values and the predicted Y values that my regression is coming up with. How am I making my predictions? It's whatever coefficient was associated with that X1 variable. But notice here, and I didn't draw it as extreme, but on the low end here, I'm going to be making errors almost in one direction. Same kind of idea up here. All of my errors are in one direction. Why? Because if I actually could draw a line that best fit this data, it's probably not linear. If I could draw any shape, I probably want it to be nonlinear. So what am I going to do if I'm running a regression and I'm trying to predict a relationship that I think is not linear? Well, linear means I have kind of y equals mx plus b. How do I make something nonlinear? I would add in a squared term, right? So now I'm still using the same variable, but I'm going to have a new coefficient that's associated with that variable, but that variable squared. Right? And I don't think we'll get there today, but eventually I don't have to just limit this to a squared relationship, right? I could actually add in a cube term. I could add in a quadratic term, a fourth. I could add in whatever I want. Now we will kind of limit it to just a squared term, kind of simplifying a little bit, but we can estimate these nonlinear relationships. Why do we want to do that? Well, at the end of the day, what do we care about? The true effect of x1 with y. If that effect isn't linear, what's going to be true about this estimate? Our predictions are going to be inaccurate, especially for these extremely low and extremely high values. So that's kind of where we're trying to get to. So if we think about nonlinear relationships, we were really estimating something that looked like this, right? If we think something's nonlinear, so I think the example that I'll pull up and state here in a second. I've got some fish database. Now what's probably true, just like humans, right? The initial years of your life, see it with my son, right? In the first year of his life, every week he's like bigger and bigger, right? His growth in terms of time, his age is like increasing at an insane rate. Now, what happens once you hit 18? Your length, right? If you're a fish or if you're one of us, your height, right, starts to basically be the same, right? There's definitely a nonlinear relationship with your physical size, right, in terms of your height and your age. Same kind of thing for a fish, right? So we know inherently sometimes that these relationships we have are not linear. We know they should be nonlinear. And that's what we want to estimate, right? So I know that it's probably a positive relationship. So if I run this regression, this is where maybe I'll usually put some of this regression code in the do file. We may not like go through every line by line for the do files now that we use, because if it's something simple like this, we hopefully are used to these simple linear regressions. We can just look at the output. So if I run this regression of length on age for the fish, sure enough, as the fish gets older, it gets longer, right? Or it gets bigger. And highly statistically significant. Well, this is kind of the problem, right? I mean, I've got a test statistic of 41, a p-value of 0. This looks like, okay, I've got a statistically significant relationship. Everything's all well and good. But just because I found a statistically significant relationship, it doesn't mean that it's the right kind of function, right? Or the right functional relationship. So if I look at this regression, if I'm trying to kind of draw lines that best fit this data, I kind of notice like, maybe if I could, I'd kind of want to have some curve to it, right? I can't get a line that exactly best fits this data. I can get lines that fit it better at certain points, but I can't have one single line. So what would I probably want to do is have some curvature to that line, right? Or add a quadratic term, okay? So if I can include a quadratic term, well then, before where most of my errors I was making were all in one direction, now my line is kind of splitting the data, right? Or if that's scatter plot data, I'm kind of getting a line that's exactly in the middle of those actual y values, so that the expected value of my error term, which is what it should be when I run a regression, the expected value of my error term should always be 0, right? On average, my predictions are accurate. For any one observation, I might have a negative error or a positive error, but on average, my error should be 0. Well, we can't do this if we force it to be linear, and so that's why we want to allow it to be nonlinear. Okay? So I kind of already discussed this idea about why, in the case of a fish and how long it is, we'd want to include that squared term. Now, here's where it gets a little bit, I don't want to say tricky, but different than what we've looked at up to this point. Usually beta 2 was like the coefficient associated with my second variable. Well, now notice beta 1 and beta 2 are both for the same variable. It's just that beta 2 is for the squared term. So when we make this relationship nonlinear using a quadratic term, we now have two coefficients to worry about. So if I think about this, jumping the gun a little bit here, but I think you guys, sometimes I think it helps to see the bigger picture. If I have just a simple linear regression, and here, I don't know, I was doing what, length, and my X variable was age, right? Really, why was that coefficient telling me the relationship between X and Y? It was actually telling me the marginal effect. What do we care about in economics? Margins. We make decisions on the margin, right? So if this marginal effect, what am I really doing? I'm taking a derivative of this function in respect to that variable that's changing, or a derivative of length here in respect to age. Okay. Now, when I do that from a simple linear regression, all I was left with was the coefficient, right? That's why we could use that coefficient to then make predictions for different ages here, the length of the fish. Now, our marginal effect is a little bit more complicated if instead I'm trying to predict this using a nonlinear term, so age and age squared. Now, when I look at my marginal effect, I'm taking a derivative of this function, length, still in respect to age. So I'll have what? Beta 1. But what's the derivative of my second component now? 2 times beta 2 times age. So my marginal effect, or the change in length because of a 1-unit change in age, will depend on, well, it's not just one value. It now depends on the age of the fish, right? So my predictions, the actual marginal effect will now be a function of the values of that variable, okay? So if I was thinking kind of before, when I had my marginal effect, at every single age, if I wanted to graph out instead, not the Y values, but my marginal effect, it was simply one value. Now it's going to be whatever beta 1 is. And here I think I'll draw it assuming beta 2 is positive, although I think in the context of our example, it's likely going to be negative, but same kind of thing would apply. Now that marginal effect, right, is going to be something different depending on the age of the fish, right? My actual marginal effect will vary. It won't be the same value for every single age. It's actually going to be higher for different values of age or lower for different values. Or if that second derivative was, right, if beta 2 is negative here, or beta 2 is less than 0, then our marginal effect is actually decreasing with the age of the fish. So we're thinking about before, we were kind of forcing that marginal effect to be one value, regardless of the value of X. Now it can be increasing or it can be decreasing, depending on the sign that's associated with that square term. So once again, I kind of could cheat here because I had an idea about what the relationship was. I'll come back to that in a second, right? When we're looking at length and age, I probably know that beta 2 is negative, right? That this fish is growing, but at a decreasing rate, right? So that second derivative is negative. So sure enough, if I looked at the results, if I included a squared term, now, how would I create this in Stata? If I want to create a new variable that is just age but squared, what would I do? Just take that variable and square it or multiply it by itself, right? Both things would do the same. So I have to create a new variable that is now representing the squared term of this variable. Okay? So that's what I did here. I've got age squared. When I include that in my regression, sure enough, there's a positive relationship between age and length, but length is increasing with age, but at a decreasing rate, or my marginal effect, the older the fish got, the marginal effect was actually getting smaller, right? So that second derivative was negative, so my marginal effect is not one value, like when I treat it as linear, the marginal effect is actually getting smaller and smaller as that fish gets older. So we can pick that up simply from our regression output. Now, what would tell me if I should be using a squared term here? What would I actually want to look at in my Stata output? So if it was in fact nonlinear, what should be statistically significant here? If it's just linear, then my coefficient on the linear term that's not squared will definitely be statistically significant. If it's nonlinear, well, what would have to be statistically significant if in fact the relationship was nonlinear? The coefficient on my squared term. Is the coefficient on my squared term statistically significant at every level here, right? The p-value 0. So this would be strong evidence that when I include the squared term, it is statistically significant that this relationship likely is nonlinear, right? That squared term has statistical significance, or it looks like, right, I can say that it's different from 0. If I couldn't say it's different from 0, then really what am I saying? Well, if I run this regression, if I fail to reject the null for the squared term, I can't say this is any different from 0. If this is 0, what does my regression become? The old linear regression, right? So what we're really looking for is there statistical significance on the coefficient associated with that squared term? Here was an example where we had that, okay? So what we could say, with any level of statistical significance, this is likely a nonlinear relationship, okay? What's another thing that should have increased if I include the squared term?
R squared.
R squared. So we get a little tricky here. Yeah.
Adjusted R squared too.
Yeah. So you're anticipating where I'm going. Anytime I add another variable, it works the same way if I add another exponent of a variable. If I add the squared term, and adding in additional information, what has to happen to my R squared? It goes up, right? It's almost like I'm adding a new variable. We can think of it the same way. However, if I shouldn't have been including that squared term, what's going to happen to my adjusted R squared? It would actually be a little bit lower than before. Now, if it should be a nonlinear relationship, then what would also likely happen to my adjusted R squared? It would go up. So if I go back, and I skip some slides, I'll come back to them here in a second. If I go all the way back here, what was my kind of adjusted R squared? 0.7032. I had a fairly large data set, so there wasn't a big gap between my R squared and adjusted R squared. When I included that squared term, we said the R squared should definitely go up. And if it should be a nonlinear relationship, it's likely my adjusted R squared would also increase. Now, we already kind of know it likely will because we saw that the added variable was statistically significant. So when we look at the squared output, not only do we see our R squared go up, our adjusted R squared from the new model is also higher, right? Suggesting it's more accurately capturing the relationship between this Y variable and the X variable. Because it's still just one variable here. We've just included the square term. Any questions on this idea before we keep moving? So I'll go back through some stuff I skipped here, right? But we just estimated a relationship where the first coefficient was positive and the second coefficient was kind of negative, right? So we were thinking about, we kind of had this concave relationship. Now, this is where it gets a little bit tricky with data, because just because we have a concave relationship, we might only see in the data, scatter plot like might just be right here, right? So we might only ever see this portion of that curve, or we might only ever see this portion of that curve. But anytime we have kind of this concave relationship, that's going to be from when we have kind of this second derivative being negative. And anytime we have this convex relationship, even if we're only seeing in the data this portion of the curve or this portion, we know that second derivative will be positive. And we'll talk a little bit about turning points in a second, but we're going to walk before we can run here. Okay. So we kind of already went through this. We said we saw that it's increasing, but at a decreasing rate. Once again, you guys have all taken the intro micro courses. What is this going to look pretty similar to? What else, when you're drawing just the basic cost curves of a company, what looks like it kind of has this, say, convex relationship? Anytime you draw a marginal cost curve, it looks like, I always tell my students, looks like the Nike swoosh. Okay. So what would be true about our marginal costs? They're increasing, but at a decreasing rate. So if we're ever using company data to estimate their marginal cost curve, what should we always be including? Square term. So we're starting to think about when you're thinking about supply, demand, when we move on from treating them simply as linear, right? And they actually kind of have some curvature. We can do that using data. We can look at prices, we can look at output. Anytime we want to estimate a demand or supply curve, we should actually be including square term. So just trying to kind of relate it maybe to some things that have seen in other classes. But, right, so we've got left off, we had this square term added. We can now estimate these nonlinear relationships. You know, I don't know. I threw this in there. You know, maybe exam performance is a function of how much you study, right? So what do you think the linear, right, component of that relationship looks like? You study more, your exam performance should hopefully. So that first kind of linear term would have a positive coefficient. But is the first few hours you put in, is that going to help your exam performance more than when you've already studied for 50 and you go from 50 to 51? Likely yes, right? I mean, I would argue the first hour you study is going to have the largest impact on your performance. If I've already studied 100 hours, for me, sometimes it can actually have negative impact, right? So we know that it's going to be increasing, but at a decreasing rate. So if I ran this regression of exam performance and how many hours you studied, that squared term, I would likely see a negative coefficient. So we can start to think about different variables having these nonlinear relationships. And this would really look very similar to what we just talked about with fish, so we don't need to kind of draw this out. I would just kind of think of additional examples to kind of give us some reference points, okay? So let's think, I think I probably already kind of mentioned this a little bit, but when I'm looking at my data output, I want to be able to look at that statistical significance of that added square term, right? That tells me if it's statistically significant, I probably should be including the square term, and that relationship is in fact nonlinear. So I had some data. It wasn't exam performance and it wasn't hours studied, but it was something like effort was like self-reported hours a week that the students studied. It was high school students, and math scale was like some math test they like standardized, you know, I-step or something like that. So we could actually see, should I be treating this? Maybe my intuition is wrong, right? Maybe this isn't a nonlinear relationship. So what we could kind of do is first go through and see, if I add a squared term, does the coefficient on that squared term have a statistically significant relationship with our y variable we're trying to predict? That's our first piece of evidence, right? So we can kind of take a look at that. The second thing we would want to do, well, we can look at our r squared. If our r squared goes up by a significant amount, well, we always know it's going to increase, but if it increases by a lot, that's probably a good indicator that this nonlinear relationship was also better at estimating the relationship between x and y, right? What's probably better to do is not just kind of look at our r squared, but also our adjusted r squared. Well, what did we kind of have that compared the r squared from two regressions as well? We were doing joint significance testing, which really was looking at, did the unrestricted r squared compared to the restricted r squared increase by a statistically significant amount? We can kind of do a similar thing as we add in squared, cube terms, and things like that. So we kind of have multiple ways we can test for statistical significance. So we'll use this example to kind of make this point, right? So I've got this effort variable. Like I said, we can think about this as like hours studied, and I have performance on some test. So sure enough, looks like non-squared, or the linear term, is positive and the squared term is negative. But what levels could I actually say I should be estimating this as a nonlinear relationship? So if I look at that squared term,
the p-value is quite high.
I wouldn't say it's necessarily high, but it's high enough to where I can't say it at all levels, right? So what levels could I actually reject the null?
The 90%.
90% and 95, right? Now I can't quite reject it at the 99 because my p-value is not less than 0.01. So with 90 and 95% confidence, I could say this relationship looks like it's nonlinear. Now, what is that really saying? When I'm rejecting the null, what I'm rejecting is that second coefficient is equal to 0. So just to kind of put it in a different context, when I'm trying to predict this math score, and I run this regression where I had this effort variable, and I also had the effort variable squared, when I was thinking about at the 99% confidence level or 1% significance level, that gave me an alpha of 0.01. Because our p-value was not less than alpha, right? 0.025 was not less than 0.01. I would actually be failing to reject the null for the squared term. Well, failing to reject the null, what am I failing to reject? We always start out assuming every coefficient is equal to 0. So if I fail to reject this as 0, what am I really saying? The relationship between these two variables is, well, anything times 0 is 0, so I'm saying it is linear. So if you fail to reject the null on that squared term, you're really saying this should be estimated as a linear relationship. Right? Now, for us, 95% is nothing to, overlook, right? We probably should be estimating this as a non. It's not the highest level of statistical significance, but it will at least had some. Okay. Excuse me. So you can hopefully kind of start to see we're using a lot of the same stuff that we talked about, just in a slightly different context. Okay. Now, what would I also hopefully want to be able to compare? I would want the kind of nonlinear regression, so I can kind of see what's happened to my adjusted R squared and my R squared. So I think hopefully, yeah, I've put it in here, right? So we can have a side-by-side comparison. So if I estimate this as a linear relationship, my R squared is 0.05. When I include the squared term, well, my R squared has to go up, right? What's probably better, kind of said earlier, not just compare the R squared, but compare the adjusted R squared. It accounts for the fact that I had to add in a second variable here, but my adjusted R squared is also higher. So this would be another thing that kind of indicates we should have been using the nonlinear relationship or estimating this as a nonlinear relationship here. So we look at our R squared, we know it's always greater. So we could then kind of look at that adjusted R squared, probably slightly better. Yeah.
The adjusted R squared is greater, but it looks like the gap between the R squared and the adjusted R squared is greater as well. So is it just like even though the gap is increasing, the adjusted R squared increasing overrides it?
So we wouldn't necessarily say that, but your intuition is right? The fact that that gap is getting larger is telling me that simply adding the variable had a considerable amount of effect on R squared. But when I account for the fact that my regression model has an added variable, it kind of scales like how much, this isn't technically the correct way to think about it, but how much each variable explained and how much each variable explains kind of like on average is going down, right? That gap between the R squared is getting larger. So it's probably that it's not the strongest. And once again, we found it isn't the strongest statistically significant thing, right? So these are just multiple points that we have that would support including the nonlinear relationship. What you brought up would be a point that it's not the strong, right? Yes, it is higher, but because that gap is larger, it's not going to be that it's the highest statistically significant, going to be highly statistically significant by adding in this square term. I wouldn't probably ever extend it to kind of ask you about that, but you're thinking about it the right way. So the next thing I could then do, right? And I can't do this because when we talk about joint significance testing, what do I need for joint significance testing? I need more than one variable where we're saying jointly significant. So we actually need two. So I can't really do the third type of test with just a square term because if I run a joint significance test for just one variable, what am I really doing? I'm just looking at that coefficient statistical significance, right? There's only one variable. But if I want to start to look at higher level nonlinear relationships, like, well, maybe this isn't just squared, maybe this is actually a cubic relationship. So I add in this cube term, right? And that like, maybe if I study more, maybe initially like, okay, it's adding to my performance, but at a decreasing rate. But then after I study for 30 hours, I've level unlocked, right? I all of a sudden have a great understanding and now it starts to increase again. Probably not the case, but that would be kind of the story with these two variables. So we add in a cube term, maybe we think that, well, maybe this is the accurate model, right? Maybe it's not that quadratic model that's better. Maybe the cubic model better fits this relationship, right? So what I can do is I can still look at the statistical significance of this added term. I can still look at changes to my adjusted R squared, but I can now say, well, compared to the linear model, does the cubic model explain more? I can run this joint hypothesis test of whether adding the squared and cubic terms simultaneously explains more than just the linear model. So I can't compare it necessarily to the squared model, but I can compare it to the original naive linear model. So here, right, when we run these joint hypothesis tests, we're assuming that both of these variables are equal to 0. So all I can really do with a joint hypothesis test is just make a statement about the cubic model relative to the linear. So if I looked at this output, right, when I run my joint significance test here, well, first of all, before I even look at these results, if I looked at the p-values associated with these two variables I included, so this is the same thought process we should have had for joint hypothesis tests in the exam, right? If the two variables individually don't have statistical significance, what is likely going to be true when I run that joint significance test? They're going to be, they weren't statistically significant on their own. When I add them at the same time, jointly, they are likely not statistically significant either. Sure, I mean, and these, you know, that gets a little bit fuzzy when we start to get p-values that are like close to 0.1 or close to point. We've got p-values of 0.9 and 0.7. I'm going to imagine that joint hypothesis test, sure enough, our p-value is nowhere close to those statistically significant levels, right? So we actually would say that the cubic model here, we're failing to reject the null. Well, the null is that these added terms are actually both equal to 0, the coefficients. So here, if I fail to reject that, we would actually be saying the cubic model is not as good as the linear model. Now, what has also happened, which is kind of interesting, look at my R squared and my kind of adjusted R squared here. Oh, did I use different samples? No, I used the same ones. So what's happened to my R squared and adjusted R squared from the squared model or the kind of quadratic model? When I look at the cubic terms, my adjusted R squared is now way lower, right? So this would be kind of evidence that compared to the squared model, my cubic model isn't as good as that one either, right? So my adjusted R squared is quite a bit lower. I've got no joint significance. I've got no statistical significance on either the squared or the cubed term. Everything points to the cubic model sucks, right? That the linear term, the linear model is probably the one that better accurately captures this relationship, okay? Now, if I did happen to see statistical significance on my squared term, but not on the cubed term, well, then I could start to compare it to my squared model where I'm like, well, this is statistically significant when I add the squared term in, but not when I add in the cubed term. So here, if I'm choosing between the three of these models, what does everything kind of indicate? Well, I said already, the cubic model is likely the worst, right? We actually couldn't say it was doing any better of a job than the linear model. But when we compared that quadratic model, the squared term, to just the linear model, everything there was kind of pointing to the quadratic model, the squared, when we include just the squared term, that was actually a little bit better. So if I'm choosing between the three here, everything kind of points to, or at least all the statistics point to, I should be estimating this as a nonlinear relationship, but only with an added squared term, not an additional kind of cubic term. We'll go here, and I think you might have had it.
Can you just quickly explain like the last two lines again, and how to interpret the F stat?
This guy?
Yeah.
All it is when we do joint significance testing. So if we went back to that formula sheet, I had a formula where I actually didn't make you compute the F stat or make you necessarily use it on the in-class portion. But what you're really saying is, was there a statistically significant increase in my R squared given the added variables? In this context, the statistically significant increase in R squared would be from the added nonlinear terms. Well, we're assuming that there is no statistical significance, that those added terms had coefficients of 0. So if we fail to reject that, don't worry about the F statistic for a second. The p-value tells us that we can't reject at any level.
Yeah.
And so that two coefficients on these added terms simultaneously, that they are equal to 0.
So the last line is the p-value, and it's just the 90, 95, 99 confidence levels.
Yep. If we had a p-value here, that was like, say, 0.001, that would actually tell us that what model should we be using? The cubic model, right?
Yeah.
Now the F statistic, it's just a test statistic, right? It's just a different distribution than our usual individual test statistic, our usual test statistics for an individual coefficient, right? So these values will look nothing like our kind of 3 benchmark critical values. In fact, the F distribution, I always say this wrong. It's so technically inappropriate for me to do. It is not one distribution. It is thousands of different distributions based on the number of restrictions we have and the number of observations. So it's technically a set of distributions, which is why these values will be all over the place, right? And which is why I don't really ever use those when we're looking at joint significance. We're just going to rely on what also spits out at me the p-value. I'm just going to use that.
So it's more about the p-value that comes out of it.
Yes. Yep. And then did you have a question still?
So if the original variable is statistically insignificant just by its nature, does creating the squared and cubed have a magnifying effect on the adjusted R squared in that it increases it at a higher rate? Or sorry, decreases it at a higher rate?
So if it has, so the original linear term you're saying is not statistically significant. Yes. But when I add in the squared term, it is.
So I'm sorry, the squared term also becomes statistically insignificant at a higher rate, and then same with the cube. Does that have like a magnifying effect on adjustment?
It would kind of depend on the ratio of how much the R squared changed relative to how many. It would depend if I added just the cube term or if I went out to a 4th term, because if we look at our actual F statistic, part of it was being divided by the number of restrictions. And so it's really like the relative change in R squared to how many variables I added. So if we're just focusing just on the cubic, like the added restrictions would always be 2. So in that case, it wouldn't necessarily amplify, like it's not like you always know the R squared is going to be higher. It's not a guarantee that it's going to be, it could be statistically insignificant, and that value divided by 2 could be higher or lower, and still both could be statistically insignificant, right? So there's not really a good, and we don't know what direction that change will be, right? I get your line of thinking, and usually, but this is also a good point. I could run a linear regression and find that there's no statistically significant relationship between 2 variables, right? I'll give you a visual depiction of what this would look like, because I think maybe that's easier than trying to describe it in words. But let's say I had something like this. In fact, I probably should have had it even more bowed out. Like I could come up with a line of best fit where at like any portion, all my errors here, negative, all my errors here are positive, all my errors here are negative. So the linear relationship could actually end up looking like it's not statistically significant, when in fact, when I look at the quadratic, that model actually, everything would be statistically significant. So sometimes your linear, I chose one where the linear model looked at least like in each one there was a statistically significant relationship. It could be that when you run that linear model, you end up thinking there's no relationship between these 2 variables. But then when I do add the squared or cube term, now I actually see, oh, there is a relationship. It was just that the linear model was so piss poor at actually capturing that relationship that it didn't look like from the linear model there was any relationship between these 2 variables. Now, when I add those squared or cube terms in, they become highly statistically significant. But that doesn't necessarily mean that my linear term is going to become statistically insignificant or significant as well. It kind of all depends on what the shape of that curve looks like, right? Here's what I'm thinking about now that I've got kind of this quadratic term. Beta 1 is a good point. If I had something that did look like this, and let's say this was 0, this is my x variable, what would my marginal effect be? It was the coefficient on the linear term plus 2 times the coefficient on the squared term times whatever that x variable. If I had something that looked like this, where would this start out? At when x is equal to 0, this would start out at beta 1. But if I had a different drawing here, where could beta 1 be? beta 1 could actually be 0. When when I estimate that quadratic relationship, the point that it starts out at could technically be 0, which is what we assume. So we would never fail to reject that. Or sorry, we would never reject it. We would always fail to reject that. All right. So there's no guarantee that we will find statistical significance on just that linear terms coefficient. Right. It all depends on where our actual data lies. Right. I know that's not like a great, answer in terms of like, we could always say that this is true, but we don't know where that coefficient is necessarily going to be.
The only purpose of my question was to determine how reliant those cubed, squared, and individual terms were on each other. But now I know that they're not reliant really.
They're not really related, right? Because it basically parallel shifts. I could find the same coefficients on the squared and the cubed terms. Right, if I had the same slope, like parallel shift lines, but every single shift here would be a different starting point. So there really is there's not necessarily any relationship. Is that what you were getting?
Yeah, that's exactly right. Yeah.
This is way further than I'll push you guys to, but this is a good question, right? When we start thinking about what we're doing. Okay. So yeah, with time. All right. So we can also think about these when we leave out the squared and cubed terms, if they do matter, if they would have statistical significance, to kind of your point, well, what would they actually cause? If they're important variables that we're omitting, we could be creating omitted variable bias, right? So there will be some relationship when we run the naive regression, because if there is a relationship between our linear and nonlinear terms, what are we going to have? We're going to have an omitted variable bias, right? So the short answer is kind of yes. Let's see, do I have, I didn't write it down. I'll remind us of what it is. Actually might make sense here to kind of do this. So if I run that naive regression, start out here, what will my actual estimate be? It'll be the true effect plus what was our omitted variable bias, the sign of the variable we omitted, the covariance of the variable that was included and the variable that was omitted, and the variance of the variable we included. Well, here it gets kind of weird because it's the same variable, but now this is going to be x and this is going to be x squared. Right? So it would have been, what would the sign have been if I included the squared term times the covariance between those two, and then divided by the variance of the variable. So we will have this kind of omitted variable bias that's created in the linear term if we should have been including the squared term, but we didn't. And we could actually kind of put a sign to that. So just like we did before. Okay? And here I'm going to kind of look at a different example. But if I had the number of COVID cases and then the population. So I had some old COVID data from when things were really popping off. And here I have it just treated as a linear relationship. Okay, so the number of COVID cases in a county and the population. So if I was thinking about this relationship, just to, I don't know, start to think about before we estimate these, if we could try to predict, sometimes it will be intuitive, sometimes it won't be. As a city gets larger, what do you think happened to the number of COVID cases that we saw? Yeah, there's more people elbow to elbow, it spreads quicker, right? But not only having more people, am I more likely just to have more people have COVID? When there's more people in a small space, the rate at which the disease spreads is likely going to be higher. So not only will we have a positive relationship, now it's going to be increasing, but unlike all of our previous examples, it should be increasing at an increasing rate. Yeah, right? You can think of it as exponential. That's another type of nonlinear relationship that would have that same functional form. I don't think we'll get there today, but we'll actually talk about some other nonlinear relationships we can estimate not using a square term, right? So here, if I include the squared term, I would likely expect that both of these signs are positive. I don't know that for sure. That's just my intuition. The data will tell me whether or not my intuition is right. Right? So if I looked at this, now here's kind of a way that we can do this in Stata, and we'll probably dive more into like code on Thursday's class. But instead of creating a new variable, this kind of becomes like cumbersome to like continuously have to like create a new variable or just multiply it by itself. There's actually a way in your regress command that you can create the squared term without having to create a new variable. So sometimes this is preferred because if you have really large data sets, every time I create a new variable, what happens to the size of the data set? It's larger and larger, and then I have to start buying external hard drives to like save all my data sets on, right? That's annoying. So what I can do is if I use kind of this C dot, this tells Stata, this is a continuous variable, right? And I want to multiply it by itself. So this kind of pound sign is saying, take that continuous population variable, multiply it by the continuous population variable, or essentially creating the squared term. But it never actually creates a new variable in your data set. So it kind of like temporarily creates it, and so it saves a lot of computing space. This class, I'll mention some of these things. The issues that are involved with like saving computing space with coding is a whole different class entirely, right? But we have some of these things that I want to start sprinkling in because these are more efficient ways to do this, right? And I don't have to like have several lines of code. I can just include this into my regression command. Now notice when I include it, I don't actually have to repeat the population variable. It will take the population variable, put it in there once, and create the squared term in, put that in there as well. All right, so it's just a much more efficient way of coding. So if I'm looking at this, first of all, did the squared term have statistical significance? Yeah, pretty highly statistically significant, right? What's the sign of both of those?
Positive.
Positive. Our intuition was at least supported by this data set, right? Now, I don't have the linear regression to compare to, but because this is statistically significant, what likely happened to both the R squared and the adjusted R squared? Likely both increased. Because this is so highly statistically significant, it's unlikely I saw that adjusted R squared. Even though I had to penalize myself for adding another variable, it was very highly statistically significant.
So which model would better fit the like behavior of the data?
Yeah, so we don't have all the points of evidence here, right? Because I don't have the naive regression. But what's one thing here that points to that the squared model is better? The added squared term was highly statistically significant, right? That is the one thing I do have in this output that tells me that. Now, to compare it to the naive regression, I would have to actually run that and then compare the kind of adjusted R squared.
But even though like the linear one, t-value is super high and the coefficient's pretty big, doesn't matter.
Yeah, so think about it this way. It kind of goes back to the question earlier. That just because that relationship should have some curvature to it, it's nonlinear. The point where it starts out could be way up here, right? So the linear term might always be highly statistically significant as well, right? So it's not saying when you're looking at the statistical significance or the value of the linear term from your squared model, that tells you nothing about just the naive linear model at all, right? It's the combination of these two coefficients that actually tells you if this is the relationship should be estimated as a kind of quadratic relationship. Now, more often than not, if the linear term is statistically significant here, if you ran the naive model, it'll likely be statistically significant there as well, and kind of vice versa. But it's not a guarantee, right? Because when we're thinking about these lines of best fit, when I have some curvature to it, maybe that linear term is going to be up here, whereas when I estimate it as a linear, well, maybe now that coefficient went. So it really doesn't tell us anything. The thing that we really want to focus on from those squared model regressions is what that statistical significance is of the squared term. Right? Because we don't have any idea of where that actually starts out. In my earlier example, like I said, it could start out at 0. So the linear term might not be statistically significant. And that's not telling you that the quadratic relationship is bad, right? It's just, that just is where that function would be graphed, right? So what we really want to rely on here is that p-value associated with the squared term. That's what's going to tell us whether or not that squared term or that quadratic model is a better fit. And then if we could compare to the naive regression, the adjusted R squared would be the next thing. Any other questions?
So the R squared and the adjusted R squared are exactly the same. Does that imply that these are like independently perfect variables?
No, not necessarily, because if we go back to the adjusted R squared calculation, when I have a high sample size, what did that scaling factor get really close to? 1. So then we were really just subtracting that we can't explain. So when we have really high sample sizes, that gap between the R squared and adjusted R squared was getting smaller and smaller. Just got a really large sample size here, right? Like we're just dealing with really large samples, and so they happen to be very close to each other. Yep. Also, good for review. What was the other part of that scaling factor? Not just n, but we said k, which was the number of variables. What have I not included here? Any other variable, right? So as I add in more additional control variables, what's going to happen to that gap? It's going to widen, right? So the fact that I didn't include any additional controls and we have a high sample size are both going to make that R squared and adjusted R squared closer together. And technically, if I went out far enough, what could I say is true? One of these has to be lower.
Adjusted R squared.
Just a little bit, right? Out to the 4th decimal, it rounds to the same value, but we technically know it's going to be a little bit lower. Okay. All right. Any other questions on this? Okay. Our intuition was right. We can kind of see that it's statistically significant. The other thing that I want to kind of bring up here, we already touched on, is I can look at a nonlinear relationship and still control for other variables, right? So just because I'm wanting to estimate a nonlinear relationship doesn't mean I can't include additional controls. We got to walk before we can run. So just the models up to this point, I was just focusing on that one variable, but you can have multiple linear regression, right? Where you add in additional controls and still make the relationship of X1 and Y nonlinear. And this, because I make one variable's relationship with Y nonlinear, doesn't mean I have to make all of them, right? In fact, what's one variable that doesn't make any sense? I couldn't actually estimate a nonlinear relationship, one specific type. Starts with the D,
Dummy variable.
dummy variables, right? Because if I take a dummy variable and multiply by itself, 0 times 0 is 1 times 1 is. So if I did include a squared term, what issue would I have? Perfect multicollinear, right? So I can't use dummy variables. I can't make them nonlinear, right? The only variables I can make nonlinear are continuous variables, but I can still control for dummy variables in my regression. Okay. All right. So when I was looking at that marginal effect, I kind of already went through this earlier, so we got that out of the way. I could just think about what that derivative would be, and this would be kind of my marginal effect of X1 here. So if I have this marginal effect, it depends on the value of X, right? So sometimes we'll kind of have this nice thing where I could think about, all right, well, if I know that this is the marginal effect equation, I can get the coefficient on the linear and nonlinear term from my state output. So I could go back here. I've got what? 1271 and 0.132. I could then plug that into my marginal effect equation and start to make predictions for what would be the impact if I had one more person, or that population variable went up by 1 unit, but at different values for X. So if I went from a population of 1,000 to 1,001 versus 100,000 to 100,001, right? So I kind of used as a sample example here, you know, one doesn't make a whole lot of sense when we're looking at population. So what would I probably want to look at? Not just a 1 unit change, but maybe like 10,000 additional people. I'd probably want to scale that variable. So I started out with like Bloomington. So if I'm thinking about it in terms of tens of thousands of people, that population variable, Bloomington would be represented by an 8. Right? It has about 80,000 people. So what would have an additional 10,000 people in Bloomington? How much would that change, or what would the marginal effect be on the number of COVID cases? Well, I take the coefficient on the linear term. That was the first part of my marginal effect, plus 2 times the coefficient on the squared term times the value of that X variable. Now here we scaled it, so 8 would represent our 80,000. Right? So if I have 10,000 additional people in Bloomington, the number of COVID cases only went up by about 1,273. Now, if I have Indianapolis, right? And here, I think I like grabbed this from some BLS data source. It doesn't like include the metro, it's just the city itself. I think it was like at 2 million people. So their population would be 200. Well, I'd have the same marginal effect equation. The only thing that's going to change is the value of X is no longer 8, the value of X would now be 200, right? So I can see there having an additional 10,000 people in Indianapolis would actually increase the number of COVID cases by about what, 50 people more? I'm looking at the difference there. So my marginal effect is getting larger with these larger population values. Or my marginal effect, when I make it nonlinear, depends on the actual values of that X variance. Questions here? Now it's not a whole lot higher. I mean, 50 people is 50 people, right? It's still, you know, increasing it at statistically significant levels. But different models we have, we might see like if that second coefficient is a lot larger, we might see very different marginal effects for cities of different size, right? So I tried to kind of plot out what that marginal effect looks like. And I kind of drew some hypotheticals earlier without example or without like numbers to it. But here, if I estimated what that marginal effect was for cities of different population sizes. Now remember here, this is representing like tens of thousands. So here was like Indianapolis, here's like New York, right? The marginal effect of having an additional 10,000 people, that's going to increase the COVID spread a lot more in a city like New York compared to Indianapolis. So because we had that kind of positive coefficient on the squared term, our marginal effect started out, the linear term was positive, it was like 1,200, but that marginal effect is increasing at an increasing rate, okay? Right, it's getting larger and larger as I have kind of higher and higher populations. Okay. Or what it's representing is that, sorry, the relationship is increasing at an increasing rate. We're on time, okay. Oh, let me think what I want to do here in the context of, okay, I think this is interesting. So any questions here before we keep moving? So I'm gonna do a similar thing. I don't know. I had this like, you don't like sports, bear with me for a second. But I do a little bit of research, not much. That's not really my role here. I'm primarily a kind of teaching professor. But I was interested, so I had some other people I was friends with, and we were thinking about, there's this thing called the Yerkes-Dobson's theory. It might show up in some of your econ courses. I don't know if they'll ever bring it up, but like upper level, like intermediate, upper level micro might talk about this. But it's the idea that when I focus on a task, so the initial thing that I got interested in, my brother's does like human performance stuff, and they had these people take a mouse, and when they were trying to get this mouse and they had to like move it to be on a dot on the computer screen. And then they were saying, okay, if you can get it right on the dot, that's a success. And they told them that. So what they found was like people were really good once they figured out the movement with their hand. They were really good at repeating this, right? But they became much worse when they were told, okay, if you get the dot this time, you're going to get $10. It's added pressure. People did worse. And then when they told them, okay, if you can get the dot this time, we'll give you 20. Well, there's even more added pressure. What do you think happened to the success rate after that?
Got worse.
Got even worse. Well, now initially, maybe going from 0 to 10, they actually did better because they actually were like, oh, I'm not just moving a mouse on a screen, I actually might get something. But as it became more and more of a pressured situation, they got worse and worse. So there's this idea that when you focus on a task, initially your performance starts to increase, but there eventually becomes a point where the stakes are so high, like on an exam, I panic, I can't think of anything, and my performance starts to decrease, right? So this is the idea of the Yerkes-Dobson theory. The more that there's more is at stake, right? Initially, that starts to improve your performance, but eventually that starts to decrease. So what do we have there? A nonlinear relationship. So I had this idea when if you watch basketball games and they're shooting free throws, right? At the beginning of the game, does that really seem like it matters to the players? No, there's still plenty of game left to play. If it's taken with 1 second left and the score is tied, so that free throw matters a lot, right? There's a lot more pressure. So we kind of have this measure of pressure by just what the score differential of the game was, and then kind of whether or not this free throw was made, just like whether or not they were successful at moving this mouse to hit the dot. So initially, when the free throw matters more, what should happen in performance? It should start to increase. They're more focused on the task. But eventually, when that score differential increases, sorry, when it gets smaller, right? Because it matters more. But eventually it matters so much, they actually start to perform worse and worse. So we might see that initially that score differential going down actually improves performance, but that when it gets too small, we actually see performance start to decrease, right? Or a nonlinear relationship. So we kind of ran this regression to kind of get at this idea. And here I've got a dummy variable. So once again, just trying to review some materials that we talked about. Here I would be looking at changes in what? The probability that the free throw is made, right? So I can kind of run this regression. I had this win probability added. It actually took not just the score differential, but it took like what the difference in the score was, how much time was left in the game, and really tried to put a value to like, how important was this shot, right? So initially, when that shot became more important or the win probability added went up, people became better making that free throw. The probability increased by 0.3. However, the squared component, as it became more and more important, what actually happened to performance, they become much less likely to actually be successful at the performance. They found the exact same thing with the kind of moving the mouse cursor on hitting the dot, right? And so here I've got kind of this increase in relationship, but it's increasing at a decreasing rate. So if I wanted to kind of look at this visual, what I've really got is a marginal effect and here I had kind of that win probability added, where this is positive, but this was negative. So if I'm kind of graphing out for different values of that X variable, what was the probability that the free throw was made, or essentially the predicted Y value? Initially, it's increasing, but at a certain point, it starts to decrease, right? There's a point here where now my performance actually starts to become negative, right? Or the change in my performance starts to become negative. So we can pick up relationships like this using output, like running regressions in Stata. I've got the square. I also have additional controls I can throw in. So I eliminate even more omitted variable bias. So I'm really guaranteeing I'm accurately capturing this nonlinear relationship. Okay. And here, I don't even think I showed everything. I've got like the position of the player, freshman, senior, sophomore, what division of basketball they were in. And you can do this with like sports. You could do this with really any type of human performance. Right? And what you find is kind of a similar thing. Right? What did I want to show here? Is this the exact same regression? No, what did I do? Division attendance, free throw mid. I don't know what I did here. Oh, I added in like kind of game seconds to really kind of get at this. It's the same kind of thing. I find a positive and negative relationship. We'll just kind of focus on this one for the sake of what we're talking about. But what's going to eventually happen if my linear term has a positive value and my second term has a negative value? Eventually that marginal effect is going to become negative, right? So where would it become negative? Well, this example, so we have our marginal effect. Beta 1 plus 2 times beta 2 times whatever X variable we're looking at. For us, we're just looking at kind of WPA here. This was 0.311. This was negative 2.87, if I'm rounding a little bit. Well, how would I figure out where the marginal effect becomes negative? What win probability added value or what X value would this be equal to 0? That's where it would switch over. So I can find where the marginal effect goes from being positive to not positive when I have these nonlinear relationships. So in this example, all I'd be left with is a little bit of algebra here. Right? So I've got 0.311. If I multiply this by 2, I'm looking at what? About 5.7, negative 5.7. Right? Times whatever that X variable is. Now it's just a little bit of algebra. 0.311 is equal to 5.7 WPA. By both sides by 5.7. And I get my turning point where that marginal effect on performance goes from being positive to negative would be, well, what did these represent? The coefficient on the linear term divided by 2 times the coefficient on the nonlinear term. Now, anytime these are the same sign, where's the turning point gonna be? It actually wouldn't exist unless I could have negative values for the variable. So sometimes we don't have turning points, especially when those coefficients are the same sign, because most variables we look at are positive, right? In this case, when we have different signs, we might actually have a point where that marginal effect, maybe it started out for low values of X as positive, but eventually it becomes negative. Now, if it's just some dumb basketball game, maybe I'm not that concerned. But when it comes to something like, I don't know, financial consultants choosing the right stocks, there's actually similar research out there that shows like when it's deals that are worth more money or when it's like more risky investments that initially they do better, but then at a certain point, if it becomes such a stressful investment that these financial consultants actually start to do worse, what does that mean? They're costing somebody money, right? So we don't have to just look at this in the context of like a sporting game or a human performance. Human performance could be picking the right stocks, making the right investments for a company, right? So I don't know. I thought that this year adopts and things, like I said, it's a more overarching kind of economic principle. I try to tie this class into what you might see in more of a typical economics course, not that's just as data driven, but we can start to think about these marginal effects where they go from positive to negative by simply figuring out where they equal to zero or where they are equal to zero. So that's why I brought this up, kind of thinking about where that turning point would be, right? If I were to graph out the marginal effect, what value for this X variable does it become negative? So we can do things that are similar to that, okay? All right, so I'll probably touch on this a little bit next class. We'll look at some other nonlinear relationships. Kind of stray away from what we talked about today, looking more at what we call like logarithmic relationships. We'll dive a little bit deeper into stata because the logarithmic stuff is a little bit different in stata. And so we'll take a little more time to look at some of these data sets while we actually code this. I'll have your exams to hand back on Thursday. Also, you know, to add some incentive, I don't know, maybe making class attendance, maybe something you focus a little bit more on. Probably have an in-class quiz on Thursday as well. We'll also be getting your exam back. So I would expect to hopefully see some smiling faces at me than I did today. Okay. If you haven't gotten it done already, get the take-home portion of the exam submitted by the end of the day today. Otherwise, I will see you guys on Tuesday or Thursday.
They didn't show you the grade.